Buenas tardes a toda la membresía de la Sociedad Mexicana de Electroquímica. Su servidora, Citlali Gaona Tiburcio, vicepresidente del Comité Ejecutivo de la Sociedad, les doy la más cordial bienvenida a las actividades académicas de esta sociedad, iniciando con los Seminarios de Invierno 2023. Estos seminarios forman parte del proyecto 317614, impulsando la promoción, difusión y divulgación de la electroquímica en México, aprobado por el CONACYT. Estos seminarios han sido organizados por el Comité Ejecutivo en curso y la División de Electroquímica de Materiales, por sus líderes, los doctores Luis Mendoza y Jorge Vázquez. Pasaremos al primer seminario, el cual será moderado por el doctor Luis Mendoza, quien también presentará al ponente, doctor Alejandro Franco. Gracias a todos. Adelante, doctor Mendoza.
Muchas gracias. Muy buenas tardes a todos. Es para mí un placer darle recibir al doctor Franco y a todos los participantes en esta serie de seminarios. Y también es un orgullo inaugurar esta sesión de seminarios. Sin más preámbulos, voy a presentar al doctor Franco porque es bastante interesante lo que nos va a comentar y no quisiera quitarle mucho tiempo. El doctor Alejandro Franco nació en Argentina y es profesor titular de la Universidad Picardie-Jules Verne en Amiens, Francia, y es miembro honorario del Instituto Universitario de Francia. Es titular de una beca de consolidación otorgada por el Consejo Europeo de Investigación por su proyecto Artistic sobre la digitalización de procesos de fabricación de baterías basado en modelado multiescala e inteligencia artificial. También ha logrado atraer financiamiento del Consejo Europeo de Investigación hacia su proyecto de pruebas de concepto, denominado Smartistic, en donde se proporciona asistencia de los fabricantes de baterías que utilizan realidad mixta. También es chairman del grupo de expertos de digitalización, métodos de medición y calidad en la red europea de líneas de piloto de baterías FlyPlanet, y además ganó el premio francés a la innovación pedagógica 2019 por su uso de la realidad virtual para enseñar ciencia de las baterías. Entre tantos logros que tiene, estos son algunos del doctor Franco. Muchas gracias por aceptar la invitación. Bienvenido y adelante, por favor.
Bueno, muchas gracias, Luis, por la introducción y bueno, muchas gracias a todos por la invitación, en particular a Jorge. Bueno, es un placer para mí estar aquí hoy de manera virtual y bueno, voy a compartir mi pantalla. ¿Ven mi pantalla?
Ya se ve.
Perfecto, muy bien. Bueno, voy a comenzar por contarles una historia. En el año 2006 fue el año que di mi primera charla sobre mi trabajo en español, o sea, soy argentino. Y luego de mi charla vinieron dos personas durante el coffee break a hablarme y decirme, bueno, su charla ha sido muy interesante. ¿Dónde aprendió a hablar español? ¿Sí? Esta gente pensaba que no era argentino, que el idioma español no era mi idioma materno. Y bueno, porque ahí me di cuenta que realmente la manera, o sea, no estaba acostumbrado a hablar en español sobre mi trabajo, ¿sí? Así que voy a tomar la libertad hoy de exponer mi trabajo en inglés, ¿eh? Si ven alguna dificultad sobre ello, les pido por favor a los organizadores que me lo digan y lo intentaré en español, pero comienzo en inglés, ¿sí? So I'm going to talk about a digital twin for optimizing the manufacturing process of lithium-ion batteries. And this is a work that we are performing in the context of a project called Artistic, okay? In this project, we intend to develop a digital twin of the entire manufacturing process of lithium-ion batteries. So first of all, I'm going to introduce a little bit, what is the battery manufacturing process about? So first of all, as you know, in a lithium-ion battery cell, so we have electrodes. So these electrodes are constituted by a mixture of materials, so the active material, carbon additive, binder. And the electron microstructure, that means the way that these materials and the pores inside the electrode are going to be organized in space, is going to control the practical properties of the lithium-ion battery cells, such as the cell energy density, the power density, the lifetime, and the safety. We should highlight here that the electron microstructure is strongly determined by the manufacturing process of the electrodes and of the cells. And the manufacturing process of the electrodes and cells is very complex because it involves multiple parameters, multiple steps and multiple parameters, which are very difficult to tune, right? And the consequence of this complexity is that we used to face high trial and high scrap rates, right? Which are actually comprised around 5% for battery production and 30% in prototyping, when we are intending to prototype lithium-ion battery cells before going to the production. And this is because usually this battery manufacturing process is optimized based on trial and error approaches, which of course they are very time consuming and they are very costly, right? This is why the concept of digital twin is emerging very strongly, in particular here in Europe since some years. And the idea here is having digital twin working hand by hand with the real machines manufacturing the lithium-ion battery electrodes and cells. So this digital twin is a digital copy, it's a copy in the computer of the real process. And the idea is that we have sensors in the real machines fabricating electrodes and cells, collecting data, for instance, measuring the thickness of the electrode being produced. This data is being sent into the digital twin where the data is being processed. And then so instructions are being provided via actuators to the machines in order to allow them to fine-tune the parameters in an autonomous way and to produce electrodes with the desired thickness or the desired quality, right? In order to avoid, for instance, the formation of cracks upon the drying of the slurry, leading to the formation of electrode. So the idea then is having this digital twin working hand in hand with this real manufacturing process. So it's basically like if the real manufacturing machines are robots and the digital twin is the brain of these robots, right? So in the context of the development of a digital twin, so we could wonder if a digital twin then is a kind of real copy, you know, actual copy or detailed copy of the real machines that we have in a prototyping line or in a production line of lithium-ion battery cells. We could imagine doing so. We could imagine programming the computer a 3D representation which looks very similar to the real machine geometry, functionalities, and so on and so forth. Well, this kind of approach is very challenging and is not generally known because, first of all, to describe in an extremely similar way a real machine using a computer, so yes, it's probably impossible because in a machine there are a lot of details going on. And in other words, also I think it's very challenging because the approach is not generally known, because you can imagine that we have different machine providers depending on the different labs, depending on the battery producers, and so on and so forth. This is why in the context of my research, we are developing machine agnostic process models. So we are developing models which are in the brain of this digital twin, which are able to predict how manufacturing parameters all along the manufacturing process are going to impact the electron microstructure and the cell properties in terms, for instance, of performance, right? So what we are doing in my group is modeling of the manufacturing process and not modeling of the machines producing the electrodes, producing the cells, okay? And we are doing this work in the context of the artistic project that I introduced at the very beginning. I was introduced by Luis. And in this project, so what we are doing is we are developing two types of models, which are actually the brain of the digital twin. So one of type of models is this so-called physics-based process modeling, where we are describing the physics going on all along each step of the manufacturing process and dealing with the formation of electrodes and dealing with the performance of the cell. And also we are developing machine learning models, which are very useful to unravel correlations between electrode properties and manufacturing parameters. And we are feeding into these models experimental data being collected in the pilot line that we have in our laboratory. So we have a pilot line mimicking how we manufacture lithium-ion battery cells in industry at a reduced scale, right? Thanks to this pilot line, so we can generate a lot of data about the influence of manufacturing parameters on electron and cell properties. And then we use this data in order to validate the physics-based models, but also in order to feed with data the machine learning pipelines are revealing correlations between manufacturing parameters and electron and cell properties. I'm going to show you examples of what we are doing for each of the steps of the manufacturing process. And the very first step is the electrode slurry at the drying of this slurry, which is going to deal with the formation of the electrode, right? When you pass the slurry through the oven. So in order to model the slurry by using the physics-based approach, because once again, in the artistic project, we are developing physics-based models and machine learning models. So if we speak about the physics-based models, we model with this physics-based approach the slurry in the following way. So we imagine the slurry to be composed of a composition of different particles. Some of these particles, they will represent the active material particles, NMC 111, for instance, here. Other particles will be fictitious particles representing aggregates of carbon additive particles, binder and solvent. And then so we are going to describe interaction forces between these different type of particles. These forces can be attractive or repulsive, or we can consider also both, having at the same time attractive and repulsive forces. And then so we implement the mathematical expressions of these forces into Newton equations, and then we solve so a classical MD-like, molecular dynamics-like framework in order to calculate the acceleration of these particles, and then by integrating the acceleration, we can calculate the speed and the position of the particles. And by tracking the evolution of the energy, when you describe the interaction between these particles in this simulated slurry, you will be able then at the end to converge to a global energy minimum, which will actually correspond to the equilibrium state of the slurry, which will represent actually the digital twin of the slurry in 3D. So this is in periodic boundary conditions, this digital twin of the slurry. And here, so in red, you see the CVD particles containing, once again, carbon, binder, and solvent. And the other particles with different colors corresponds to the active material particles having different sizes. So the input of this model is going to be the formulation, that means the ratio that you have in weight percentage between active material, carbon, and binder. Another input will be the particle size distribution of the active material. Once you get this digital twin of the slurry, so you can calculate in the computer properties that can be measured experimentally. For instance, the density of the slurry and the viscosity of the slurry as a function of the applied shear rate. And then so with a lot of back and forth between the calculations and the experimental data, you can determine actually the parameters that you need to put in the force expressions, the force field expressions, in order to describe correctly the viscosity and the density of the slurry. And in order to do so, what we do is we fit the density values that we calculate with experimental ones, and we also fit the viscosity values that we calculate for different shear rates with experimental ones for different slurry formulations, different solid contents. And in order to fit the parameters, so we adopt a combination of optimization techniques, combining in particular two techniques, particle source optimization and Bayesian optimization, but also machine learning, okay? We have published last year a paper where we report a machine learning pipeline which is able to predict the results of these physics-based simulations in terms of viscosity and density before the physics-based simulation finish. In such a way, so we can forecast, we can predict the results of the physics-based simulation without the need of running this physics-based simulation until the end, by knowing that a physics-based simulation like this can be very time-consuming. In such a way, thanks to this machine learning model, so we can accelerate the optimization of the parameters that we need to put in the force field in order to match correctly the viscosity and the density values from experiments. I'm not going to discuss in more details this slide, which is very technical. It relates a lot to machine learning in particular. So if you have questions, of course, I will be happy to discuss this in more detail. So I prefer to get progress in the description of the different models that we have developed for different steps of the manufacturing process. And the next step is the drying, okay, the physics-based model of the drying process of the slurry. In order to simulate this process steps, so we start with the slurry microstructure that we have predicted using the particle dynamics framework that I described before. Then we shrink the size of the CVD in order to mimic the fact that the solvent is going away when you dry this slurry. And then so these green particles representing the CVD, so now they're represented in yellow. And then we run the MD-like, molecular dynamics-like framework again by solving Newton equations, by once again describing the interaction forces between the particles, and then we converge to a new equilibrium state, which will represent the dry electrode microstructure, where you see in yellow the carbon binder domain, in this case not containing any more solvent. It contains just carbon additive particles and binder, and you see in red the active material particles with different sizes. So this virtual representation of the electrode, digital twin of the dry electrode, can be characterized in the computer in terms of properties that we can measure at experimental level. For instance, the porosity of the electrode and the tortuosity factor of the electrode. But also we can characterize other properties such as, for instance, the conductivity, electronic conductivity of the electrode, and so on and so forth. So I would like to highlight, here you see this paper, Journal of Physical Chemistry Letters in 2017. So this is a paper that we jointly published with Jorge Vázquez Arenas, who is present in the audience and who is organizing this event. And we host Jorge for 3 months, and we had a very nice collaboration. And he was in charge of modeling the electrochemical performance of this electrode being produced, being generated by this simulator of the manufacturing process. And since then, so we have also had a lot of progress in the methodology and so on. And one of these progresses is that now we are able to simulate the impact of the drying rate on the electron microstructure in order to capture the influence of drying rate on the CVD migration phenomenon, which is a phenomenon widely known in battery manufacturing. When you dry too fast the slurry, what you observe experimentally is that you will have a lot of carbon binder domain going on top of the electron. Okay, and this will be a problem because you will have an isolating layer between the electrode and the separator that I'm going to put on top of this electrode. Here, the simulations are performed by shrinking the CVD at different rates, depending if you are talking about the CVD near the separator or the CVD which is in contact with air. CVD here stands at the slurry phase for carbon binder containing a solvent domain, right? When you shrink the CVD at different rates, so then by playing with the rates of shrinkage of these different CVDs at different zones, you can converge to electron microstructures with carbon binding domain, with house solvent in this case, with different repartitions along the electrode thickness. And in particular, if you apply high drying rates, you will start to see a lot of gradients of CVD content along the electrode thickness, in good agreement with what we can find at the experimental level. So you can also address the problem of the slurry, the drying by using machine learning, okay, and in particular supervised machine learning. And here, so I'm bringing to you a paper that we have published initially in 2019, and then so the definitive year of publication was in 2020, because in 2019 it was the accepted version of the article was published. And here, so what we want to do is to apply machine learning in order to predict the influence of slurry formulation, solid content, and viscosity on the electrode porosity. We also explore the impact on electrode loading. Okay, that's something that I'm not describing here in this slide. And then, so we were able to derive a machine learning model which is able to predict with 80% of accuracy, so the influence of these parameters on the final porosity of electrode. And here you see how the porosity of the electrode depends on the viscosity, on the solid content, and the electrode formulation, the slurry formulation. This is the weight percentage of NMC 111 in the slurry. You see that the curves here are, this collection of points is very scattered, right? It's very difficult from this graph to unravel any kind of correlation between these 3 input variables and the output variable, which is the porosity of the electron, right? So if you apply supervised machine learning, and in particular a technique called support vector machine, you can transform this collection of scattered points in something that is more understandable by humans. You can transform this scattered collection of points in phase diagrams, right? Exactly like in crystallography, right? But here for manufacturing processes. And these diagrams actually, they look like this. For instance, you see in this axis the viscosity of a slurry, which is related to the coma gap and the coating speed in your coater, okay? Coating the slurry and then goes into the oven. You see in this axis the solid content. You see different formulations here. And in colors, you have electrodes, classes of electrodes corresponding to different degrees of porosity. White means that you have electrodes with porosity lower than 30%, and blue means that you have electrodes with porosities higher 40%, right? And pink is in between, right? You see that this support vector machine technique predicts that if you use low NMC contents, then it's impossible to get electrodes with low porosity. However, if you increase the amount of NMC in your slurry, it becomes possible to make electrodes with low porosity if you choose the right viscosity value and the right solid content. Once again, this type of graph, I think is very useful, in particular for technicians and engineers working in pilot lines, prototyping lines of batteries, because very quickly, thanks to this kind of phase diagrams, they can decide which slurry viscosity they need to have. This is once again connected to the coating speed and the coma gap that you have in a coater, and which solid content you need to have in the slurry, which formulation you need to have in order to get electrodes with the desired porosity, right? Here I'm showing an extension of this machine learning approach, and this is actually for solid-state battery separators, right? This is a work that we have performed in collaboration with the group of Shirley Meng. At that time, she was working in University of California, San Diego. Now she's in University of Chicago. We applied the same machine learning pipeline in order to predict how different manufacturing parameters are going to impact the conductivity and uniformity of solid-state separators for solid-state battery applications, okay? And the combination of algorithms that we have performed is actually PCA, which is a principal components analysis, which is a very nice technique in order to reduce the parameter space of your experimental data set. Then we use K-means, which is a supervised machine learning technique in order to unravel different classes. And then we feed these classes into a supervised machine learning technique, support vector machine, in order to construct this kind of phase diagrams, which can guide you in the choice of the parameters that you need to adopt in order to fabricate the separators with high uniformity and high conductivity. Let me move now forward to the next step of the manufacturing process of lithium-ion batteries. Here I'm coming back to lithium-ion batteries. And the next step is, of course, the calendaring, okay? The calendaring consists of pressing the electrodes in order to improve the electronic contact between the particles. We need to press the electrodes to improve electronic contact, but at the same time, we need to avoid the pores inside the electrodes to be fully collapsed, because if these pores become fully collapsed, then the liquid electrolyte that you need in order to exchange properly lithium ions between the two electrodes is not going to wet properly the porosity, right? This is a very complex process step because in a calendaring machine, you can control basically three types of parameters. You can control the gap between the rolls pressing the electrodes. This gap is related to the pressure that you apply into the electrodes. You can control the speed of the rolls, and you can also control the temperature of the rolls. These three parameters are going to impact the final electron microstructure upon calendaring. And here, so I'm showing an example. This is based on data analysis, combining statistical tools and also some kind of machine learning tools, for instance, K-means. And here you see how the applied pressure upon calendaring and the temperature of the rolls are going to impact the volumetric capacity of the electrodes that are being produced upon calendaring. And you see here, there is a zone here there is an optimum, right? This is a kind of heat map. And you see the influence of the same parameters on the electronic conductivity, okay, of these electrodes. There is also another axis, which is the roll speed, okay, which is not represented here in this graph. But this is just to show you how complex can be the impact of these manufacturing parameters of the calendaring step on the final electrode properties that you get upon calendaring. How we model this calendaring process by using the physics-based approach in the artistic project. So when we use the discrete element method, which is a kind of particle dynamics method or molecular dynamics method for mechanics, right? So here, so we describe interaction forces between the active material particles, between the CVD particles, and the active material particles. And then so we simulate the effect of compression. So I'm going to play the video again on the electron microstructure evolution. In blue, you see the active material particles, in red, the CVD particles. And you see that when you compress the electrode, there is a plastic deformation, but also there is a little bit of elastic recovery, okay? And this is a phenomenon called a spring back phenomenon, okay, in the manufacturing, battery manufacturing field, which is widely known, in particular in industry, and it's very difficult to optimize. The model is able to predict the influence of calendaring on the plastic deformation, and also is able to predict the influence of calendaring in the elastic recovery or spring back phenomenon. The microstructure of the electrode being used for simulating this calendaring step is the one arising from the drying simulator. Okay, you see all these models are connected sequentially, right? And then so another point which is very important to highlight is that the parameters in these models are being determined by fitting, so the micro indentation characterizations, right, that we have performed in collaboration with University of Lille, which is near the city of Amiens, the city where my lab is located. And here, so in this microindentation experiment, so you basically use an indentator to arc into an electrode, and then you measure the resistive force of the electrode towards this indentator. And then so you can simulate this by using this method, and then by comparing results with from the model with the experiment, so then you can calibrate the parameters that you need to put in the interaction forces describing the interaction between these particles upon calendaring. And also we have calibrated these parameters at the same time, simultaneously, to compaction curves. In a compaction curve, we represent the influence of the calendaring pressure on the electrode porosity. Okay, and you see here also a very good fitting with the experimental compaction curve. We have recently extended this model. This is a paper published very recently this year, to the case of having no spherical active material particles. Okay, because probably you notice that all the simulations I show you so far with the physics-based approach are considering so active material particles as spheres, right? But in reality, this could be a quite good approximation for active materials such as NMC11. But if you start to look in detail the particle morphologies, you don't have spheres, right? You have things like that, right? Which could be represented eventually as spheres, but they are not really spheres, right? So in order to being able to simulate the systems where you don't have, the hypothesis of the spherical particle is very far away from reality. So we have characterized electron microstructures before calendaring, after calendaring, using micro-CT, microcomputer tomography. And then in such a way, we can extract families of particle morphologies. And then in each of these particle morphologies, we embed a collection of spherical primary particles, reproducing the overall morphology of a secondary particle. And then we apply the same MD-like framework I described before. That means we account for interaction forces between primary particles with different magnitudes for the primary particles belonging to the same secondary particles versus the case where these primary particles belong to different secondary particles. In such a way, so then we can simulate the entire manufacturing process, therefore the slurry, the drying, the calendaring, by using no spherical particles. And here, so I'm going to show you a couple of examples of what you can get with these more sophisticated models. So for instance, you can predict the influence of calendaring on the electron microstructure, and you can account for the deformability, the deformation of the active material particles because of the calendaring process parameters, right? The compression degree, the temperature, and so on. Here you see some quantifications of this deformability. This is a Kramer sphericity, the probability density as function of the Kramer sphericity. When you calendar electrodes, so the particles are becoming less spherical, right? Are getting deformated, right? With this model, you can also account for the cracking, right, of the particles. This is a paper that is right now under preparation and hopefully will come out soon. It's an extension of this model, which is able to predict under which calendaring conditions the active material particles are going to become crack, right? And this is also a problem in terms of manufacturing, right, of electrodes and producing electrodes in industry, right? How to optimize the calendaring process, right, in a way that you have good electronic percolation between the particles, you don't collapse the pores, and at the same time you don't crack the active material particles. And in this graph here, so you see a comparison of the tortuosity factor of different electrodes that have been simulated by using this framework as function of the porosity for a given formulation. And here we compare the case of the model accounting for spherical particles, okay, these are the circles here, with a model where we consider no spherical particles. And you see that for the no spherical particle case, the calculated tortuosity factors of the calculated electron microstructures are systematically higher than the tortuosity factors corresponding to the electron microstructures calculated with the spherical approach. And the reason is that when you have no spherical particles that are actually deformable, when you compress the electrode becomes more compact, right? And if the electrode becomes more compact, then the pore network inside the electrode is going to be more and more tortuous, right? And this is explains why then so the tortuosity factors are higher in the non-spherical case versus the spherical one. So we have applied this artistic physics-based modeling framework to different chemistries, okay, of active materials and different chemistries of cells. For instance, we have demonstrated the transferability of this approach for graphite silicon-based negative electrodes, I mean, once again, for lithium-ion batteries, where we have simulated the entire manufacturing process, that means the slurry, the drying, the calendering, and we have even predict the electrochemical mechanical behavior of these silicon graphite electrodes. You know, when silicon is being lithiated, so it expands in volume by 300%, and then you have a lot of mechanical stress that is being generated inside the electrodes. So the model is able to also capture that at the performance level. We have also demonstrated the transferability of this approach to LFP-based positive electrodes for lithium-ion battery applications. And we have also demonstrated, and it's a paper that we published last year, the transferability of this approach to some exotic active materials, such as organic active materials synthesized in-house for sodium-ion battery applications, right? And also, we have demonstrated the transferability of the approach for the manufacturing, the simulation of the manufacturing process of NMC-based positive electrodes for solid-state batteries. The difference with the three previous cases, in the case of solid-state batteries, is that you need to account for the solid electrolyte particles in the simulation pipeline, right? To simulate the slurry, the drying, and the calendar, right? Therefore, you have more parameters to fine-tune here in the force field approach, but we have demonstrated that the approach can apply and getting relevant results. For instance, we can calculate from the predicted electron microstructures the effective electronic conductivity, the effective ionic conductivity as function of the manufacturing parameters. You can address also the calendaring by using machine learning, okay? And here, so I'm going to illustrate an example of application. It's a collection of papers that we published in 2020-2021. For 2020, so it's in particular based on the CISO method, which is a method I really recommend you. It's actually a method which is trained with data, right? And which derives algebraic equations relating input variables with output variables, okay? I think it's a very cool method to derive formulas, right? Mathematical formulas that then you can apply for predicting, right? The influence, for instance, of calendaring pressure, calendaring temperature on the final electroporosity, right? Here you see a demonstration of this of application for the context of calendaring. We have first built a data set where you have as an output the porosity of electrode after calendaring, and as an input you have the formulation of the electrode, which is actually the active material contained in weight percentage, the porosity of electrode before calendaring, the thickness of electrode before calendaring, and the calendaring pressure. These are the four input variables, while the output variable is the porosity of electrode. Thanks to this data set, we have derived a correlation function, okay? This is a kind of fitting, right? Relating the porosity of the electrode as function of these four input variables. And then we have used this correlation function in order to generate a lot of electron microstructures in 3D. So we have generated a bit more than 4,500 electrodes. This generation of electrodes was performed by using a stochastic approach. That means that we are locating all these active material particles, CVD particles, and pores in a random way in the electrode volume. And then we have characterized these electrode volumes in terms of properties that have some relevance at experimental level. For instance, the tortuosity of the pores, okay, tortuosity factor of the pores, which are here assumed to be fully filled with liquid electrolyte. We have also characterized the tortuosity factor of the solid phase, which is related to the conductivity, electronic conductivity of this electrocomposite. We have characterized other properties such as the surface area of contact between active material and electrolyte, which is assuming to fully fill the pores. The surface area of contact between the solid materials, the 4 carbon binder domain and active material, and the current collector, and so on and so forth. Based on this data set, where you have as an input these 4 parameters and as an output all the collection of parameters that you can imagine for an electron microstructure, we have trained this CISO based machine learning model in order to perform regression, okay, in order to predict numbers actually, okay. And here, so I'm going to show you an example, right, of what you can get with this technique. You can predict the influence of calendering pressure, the initial porosity of the electrode, and the formulation of the electrode, okay, each curve here with different color corresponds to a different formulation, on the tortuosity factor that you will get in your electrode upon calendering. You see that when you increase the calendering pressure, so the tortuosity factor increase in these 4 cases. This is expected because the electrode is becoming more and more compact, the pore network is becoming more and more tortuous. But the nice thing with this method is that you can quantify the degree of impact. And you can also see that the degree of impact of this calendering pressure on the final tortuosity of the electrode depends on the initial porosity of the electrode, I mean the porosity the electrode has before the calendering, and also depends on the electrode formulation, right? And I believe, once again, that this kind of result arising from machine learning can be very useful for guiding technicians and engineers working in prototyping lines and in pilot lines before the production of lithium-ion battery cells. With these techniques, you can also perform some correlation analysis, and here you can build this kind of graph here that I believe is very, very useful and interesting. Here you see the influence of these 4 input parameters that we have explored in this study, and here you see the output parameters, right? For instance, if you have a red circle, means that you have an inverse correlation between 2 variables. Green circle means that you have a direct correlation, and the size of the circle means actually tells you something about the degree of correlation, right? Big circle means that you have a strong correlation. Small circle means that you have a weak correlation. If you take the example, for instance, of the calendering pressure, if you increase the calendering pressure, the porosity of electrode decrease, the correlation is very strong. So if you increase the calendering pressure, you also increase the tortuosity. The color here is green, and the correlation is quite strong. However, when you increase the calendering pressure, so you see that you increase a little bit the surface area of contact between the carbon binding domain and the current collector, right? There is a correlation, which is direct correlation, but the effect is weak, okay? Once again, this kind of graph can be very useful also for guidance, right? Because very quickly you can already have an overview of how the parameters, the input parameters impact the outputs, right? And I believe this can be transferred to any kind of problem, in particular in electrochemistry, right? Beyond the field of lithium-ion batteries. The next step in the manufacturing process simulation is considering the electrolyte filling, okay? So this, you see here a cylindrical cell, okay, of lithium-ion battery cylindrical cell, as you have in the Tesla cars, being filled with a liquid electrolyte in a glow box. This is a process which is very difficult actually to optimize at experimental level, because as we will see in a minute, so it's a very complex process, right? Here you see simulations that we have performed by using the lattice-Boltzmann method technique to predict the trajectory of the electrolyte when it's being infiltrated electrodes, an uncalendar electrode and a calendar electrode. So you see that how fast was I will play the video again, how fast is the infiltration of an electrode by an uncalendar electrode, and how slow is the infiltration by liquid electrolyte of a calendar electrode. The reason is that a calendar electrode has higher tortuosity factors. Porosity is lower, tortuosity factor is higher. Therefore, there is a more intricate path for the liquid electrolyte to go into the pore network. While for an uncalendar electrode, porosity is higher, tortuosity factor is lower, then so it's easier for the liquid electrolyte to go and to fill the pores, right? So this is highlighting that there is a trade-off between the manufacturing process step calendering and the manufacturing process step electrolyte infiltration, because in the calendering, you need to compress the electrode in order to improve the electronic contact with between the particles. But in electrolyte infiltration, it will be better to have high porosity, right? But if you compress the electrode, you will have lower porosity, you see? So then it's very important to optimize both steps by considering both of them, right? That's why this kind of modeling workflow, where we intend to capture different model tools sequentially, so it's very useful because you cannot reveal this kind of correlations between different process steps. Here you see results from this lattice-Boltzmann method simulation. This is the predicted distribution, spatial distribution of trapped air in the electroporosity. You see here a lot of air bubbles which remain inside the electrode volume after the electrolyte infiltration. And this is, of course, problematic because if you have air instead of liquid electrolyte, then your active material is not going to be fully active upon lithiation or deletion, which is an electrochemical process. You need lithium ions to arrive to the surface of the active material. If you have air, the lithium ion is not going to arrive to the active material, right? And then you will lose performance for your lithium ion battery cell. You will lose energy density, you will lose power density, right? This phenomenon is strongly dependent on the electron microstructure, as we saw here, but also is strongly dependent on the contact angle between the liquid electrolyte and the electrode. It's also dependent on the electrolyte density and the electrolyte viscosity. And these properties can be controlled by playing with the chemistry, the chemical composition of electrolyte. Okay. Here you see a result of simulation showing how heterogeneous can be the infiltration by liquid electrolyte of a cell sandwich. This is a simulation also in 3D, but here I'm showing a side view. In anode, you have a graphite-based electrode. You have NMC111-based electrode in the cathode side. In the middle, you have a separator with a microstructure arising from tomography characterization. And these electron microstructures were generated stochastically. And you see here, yes, how heterogeneous is the infiltration process if you put a drop of electrolyte on top, right? And this is because the porosities and the tortuosity factor of these three layers are different, right? This explains why it's so heterogeneous. And this also explains why it's so difficult to optimize this electrolyte infiltration process in industry, right? Why it's so time consuming. The lattice-Boltzmann method that we have used in order to explore this infiltration process step with physics-based simulations is computationally costly, okay? In order to simulate the infiltration of a single electrode, it can take you 1 to 2 days of simulation time, depending also on the computational power that you have. This is why we have derived, by using machine learning, a surrogate version of this lattice-Boltzmann method, which has the advantage to being able to simulate the infiltration process of electrodes in 3D by the liquid electrolyte in few seconds instead of a couple of days, okay? And here, so what we use as a training data set is the results arising from the lattice-Boltzmann method. And we have actually defined different descriptors. For instance, the saturation, the final saturation of each of the pores in a given microstructure, the time that the pore takes to be fully filled or partially filled, and so on and so forth. And with this data set, we have trained a multi-layer perceptron model, which is nothing more than a kind of neural network model. Thanks to this model, so we are able to predict, in good agreement with the results of the lattice-Boltzmann method, which is here standby real. We see that very good prediction with the machine learning model of the calculated saturation curves by the lattice-Boltzmann method for different applied pressures. And also, thanks to this machine learning model, we can also reconstruct in 3D the trajectory of the liquid electrolyte in the electrode volume, in good agreement with what you get in the lattice-Boltzmann method. So we believe this is very interesting because in very much reduced computational power, you can predict the same results that you get with the lattice-Boltzmann method. And this paves the way towards the high throughput screening of the influence of electrolyte properties, electron microstructures on the speed and the easiness of this infiltration process by the electrolyte of the electrodes, right? And this is actually a paper that initially we published in 2021, describing this method. And now we have a paper under review where we are demonstrating the use of this method for high throughput screening of this electrolyte chemistries and also electron microstructures in the facility to infiltrate the electrodes by the liquid electrolyte. Hopefully this paper will come out soon. The last step to digitalize the battery manufacturing process is the simulation of the electrode and cell operation, right? Once we get these virtual representations of the electrodes, this digital twin of the electrodes and the digital twins of the cells, we would like to know how these electrodes and cells are going to behave when they are going to be applied, for instance, in a mobile phone or in an electric car, which is the matter of interest of my projects, is more related to electric cars than to mobile phones, right? In order to do so, we apply a technique called final element method. This is a model actually that we co-developed with Jorge Vázquez Arenas, as I mentioned so before in 2017, and then we improve a lot with new functionalities and so on and so forth. In particular, we improve it by considering explicitly the spatial location of the carbon magnetic domain in the electrode volume. And then by performing meshing of the electron microstructures arising from the manufacturing simulation, then we are able to simulate, by implementing the physics going on when this electrode is operating in a lithium-ion battery cell, which is being discharged and charged and so on, we are able to predict the lithiation and delithiation dynamics in the 3D volumes. So as function of the C rate, which is related to the current density being applied to the battery, and as function of the temperature and other operation parameters. And here you see that the model is able to predict also electrochemical descriptors. Here you see these charge curves for different C rates, for 3 C rates, for different electrode formulations and for different compression degrees upon calendaring. And you see a very good agreement with experiments. By not changing any internal parameter in the model related to these 3 physical, chemical, or electrochemical / physical processes taken into account, the model is able to follow the trend observed at the experimental level. And this is, I believe, is also another way of validating the manufacturing simulation framework, because that means that the electron microstructures you are predicting by using different formulations, different calendar degrees, allows you to predict galvanostatic discharge curves in good agreement with experimental ones. This is a paper that we published also this year in 2023. And we are discussing this paper other aspects such as the influence of this calendaring degree or compression degree on the contact resistance between the electrode and the current collector, which plays also a role in the trend that we are reporting here, on the influence of C rate, formulation, and calendar degree on the galvanostatic discharge curve. Last but not least, I mean, we can wonder, can we use these tools for optimizing the manufacturing process? And because here I describe tools to predict the influence of manufacturing process on electrode and cell properties, but can we use these tools to predict which manufacturing parameters we need to adopt in order to have an optimized electrode, right? Well, the answer is yes, and this is also a paper that we published very recently this year in Energy Storage Materials. And here I'm showing this with an example. We have actually performed design of synthetic experiments. I mean, that means that we are performing simulations by using the artistic physics-based modeling framework of the manufacturing process of NMC 111 electrodes by simulating the slurry, drying, and calendering for different ranges of formulations, solid contents, and compression degrees. Okay, so for here we are playing with the formulation, solid content in slurry, and with the calendar degree in the calendering step by keeping fixed or constant the conditions for the drying step. We have produced, based on that, a lot of electrodes that we have characterized in terms of properties such as conductivity, tortuosity, porosity, thickness, and so on and so forth. And then we have derived a machine learning model able to predict how these manufacturing parameter values from there are going to impact the final electrode properties upon manufacturing, right? So then this machine learning model has the advantage compared to the physics-based modeling that is less computationally costly. In few seconds, you can get your answer. And then we embed it in a multi-objective optimization algorithm based on Bayesian optimization technique in order to predict which are the parameters you need to adopt in the manufacturing process in order to reach electrodes with optimized properties. This is a detail of how we are actually designing these synthetic experiments, right? We use a technique called SOBO sequences. That means that these points, these synthetic experimental points are taken randomly, okay? Between these 3 variables that we have explored here. Once again, solid content of the slurry, formulation of the slurry, and compression degree upon calendar. In this slide, you see a little bit about the accuracy, of the machine learning model able to predict electrode properties as function of these three manufacturing parameters. And you see here the R2 scores, which refers to the accuracy, right? Closer to 1 you are, so better the model is in prediction, right? Better prediction accuracy the model has. And you see here very good accuracy in the prediction of the tortuosity factor, the electronic conductivity, the active surface area, and the density of these virtual electrodes in comparison to what you will predict by using the more computationally costly physics-based model. Okay. These graphs are actually representing the same thing. So predicted values are the values predicted by the machine learning, and real values are the values predicted by the physics-based model. Okay, and the idea here is being closer as possible to this 45-degree line, right? If you are matching perfectly this line, that means that you have a machine learning model with accuracy 100%, right? Now, if you integrate this machine learning model in this Bayesian optimization algorithm, and you ask to this algorithm to optimize 4 properties simultaneously, conductivity, density, tortuosity factor, and active surface area, this Bayesian optimizer will tell you which manufacturing parameters you need to adopt in order to reach this optimal electron. And here you see the value that this Bayesian optimizer predicts for the active material content, the formulation, the solid content of the slurry, and the compression degree. This is represented here in red in terms of the properties, that are being predicted to be optimal. And if you enter these manufacturing parameters in the artistic manufacturing simulator, and then you characterize the electrode properties of the resulting virtual electrode, you will realize that these properties match very well with the predictions of the Bayesian optimizer. So this is a way of validating the prediction of the Bayesian optimizer. And this is something that we have also performed at the experimental level. So we have checked that this electrode can be done at the experimental level by entering these manufacturing parameters predicted by this Bayesian optimizer. If you optimize one single property every time, for instance, the conductivity or the tortuosity factor, the optimal electrodes will be different. Okay. For instance, if you optimize only the tortuosity, you will have an electrode with very low tortuosity factor, but also an electrode with very low conductivity, low density, and also quite low active surface area, right? These comparisons here are illustrating why it's important to optimize the 4 properties at the same time, and not only one single property, because if you intend to minimize the tortuosity factor of an electrode in order to improve the power density of your cell, maybe you will lose conductivity, right? You will have an electrode with very poor electronic percolation, right, in the electrode volume. So we believe that this is a nice demonstration of how we can use physics-based models combined to machine learning and to Bayesian optimization in order to perform inverse design of manufacturing process of lithium-ion battery electrodes. That means predicting which manufacturing parameters we need to adopt in order to get optimal electrodes. Let me conclude now in 2 or 3 minutes. So this is the slide summarizing what I show you today. So we have actually a collection of physics-based models simulating each step of the manufacturing process, from the mixing, something that I didn't discuss today, but this is a paper coming out as well, until the performance. We have surrogate models based on machine learning, predicting also the influence of manufacturing parameters on electrode and cell properties. And we feed into these digital workflows data coming from our experimental pilot line. I mean, the pilot line mimicking how we manufacture lithium-ion battery cells in industry. Okay. So we have released some couple of years ago, so in 2020 for the first time, so online manufacturing calculator. So this is a tool which allows you to simulate the manufacturing process of lithium-ion battery electrodes without having any knowledge about simulations, because we have there very nice graphical user interfaces. And these graphical user interfaces allow you to play with parameters like in experiments. For instance, the active material particle size distribution, the formulation, the solid content, and so on and so forth. And then when you choose these parameters, you launch simulations in our HPC facilities. And then when simulations are obtained, you receive an email with the results, right? You can download and you can use for your whole research. But you can also explore the data produced by all the users of this computational portal or online calculator service. So we have for now. So integrated here the slurry simulation, the drying, the calendaring, and also we have integrated the last part of last year, I mean, by the end of last year, the simulator of the infiltration process in 3D by using the lattice-Boltzmann method. And we have also released some scripts which allow you to predict the influence of manufacturing parameters on electrode properties based on machine learning. As for this month, we have more than 520 users, 25% from the industry. Many of these people, they connect, they explore the functionalities, they download data for the research. Some of these people so use this tool in order to perform simulations and then download the research. So you are very welcome to connect and to use it and to test it. I think it I hope it can be useful for your research. I believe so. It can at least help you understanding how these manufacturing parameters impact electrode properties. And also I believe that this could also be a source of inspiration in other domains of electrochemistry and not only batteries, right? Last but not least, we are working since 2016 in the development of a metaverse for batteries, okay? And here you see one of the latest virtual reality-based tools that we have released. So if you scan this QR code, you will be able to use it from any kind of internet browser, I mean, by using the mouse pad and the keyboard of your computer. But also we can use these tools by using HTC headsets. I mean, you are really in immersion in a virtual reality environment. And this is actually a serious game where you have to interact with the different manufacturing machines that you find in the prototyping line of our lab. So this is really a digital twin of our lab facilities. And then this is was developed with the purpose of popularizing the science of battery manufacturing, popularizing the kind of parameters that you need to play with in each of these manufacturing machines, and also to understand how these parameters influence electrode and cell properties. Because at the end of this game, you need to, I mean, the game asks you to characterize the electrochemical performance of these virtually manufactured lithium-ion battery cells, okay? This is a concept that we are working very strongly right now, and we are going soon to implement a functionality where multiple players from different parts of the world will be able to interact inside the same virtual reality environment to solve collectively battery manufacturing problems. This is my last slide before the acknowledgements, just an announcement. So I'm right now looking very actively for PhD students, okay? Maybe some students here from Mexico, I mean, maybe from the professors who are attending this meeting. So if you maybe know you have students, very good students that will be interested to work on the modeling, digitalization, machine learning of battery manufacturing, please drop me an email or ask your students to drop me an email with their CV. And if students are attending this symposium, so of course they are also very welcome to contact me directly. So we have an offer in collaboration with the French chemistry company Arkema, which is the widest chemistry company in France, on the modeling of the manufacturing process of lithium-ion battery electrodes. And we have 2 PhD positions in collaboration with a research institute in France called EFP New Energies. Also on the modeling of manufacturing process, but this time on sodium-ion batteries and solid-state batteries. If you are interested or you have students who might be interested, please drop me an email. Positions are to start as soon as possible, okay? Okay, thank you very much once again for the invitation and for your attention.
Muchas gracias, doctor. Muy interesante su ponencia y seguramente hay muchas preguntas, pero les voy a pedir que las plasmen a través del chat para poder hacerlas de manera ordenada. Mientras empiezan a aparecer las preguntas, yo tengo varios cuestionamientos, pero más bien son como de desconocimiento. ¿Existe algún software comercial que haga algo equivalente a lo que ustedes están desarrollando?
Muy buena pregunta, Luis. Gracias por la pregunta. No, no existe, pero estamos creando una startup para que ese software sea existente. Sí, y la idea es que la startup, o sea, estamos en pleno proceso de creación de la startup y la idea es que comience a comercializar a fines de este año.
Ok, perfecto. Entonces son pioneros en esta área y
Sí.
están formando parte de las Deep Tech, ¿no? Que es
Exactamente.
lo que ahora viene,
Exacto.
la ciencia con responsabilidad.
Exacto.
Tenemos una pregunta. de Jorge Vázquez. Dado que ustedes son muy cercanos, me voy a permitir si él la hace verbalmente.
Muy bien.
Jorge, por favor.
Thank you for a very interesting talk, Professor Franco. Well, this is a very general question for people, undergrad and grad students jumping into the world of electromodeling. What's your advice for courses or seminars
Okay.
take before going into the modeling?
Thank you very much, Jorge, for the question. So, my first advice will be to be, open-minded. Okay, not having fear about modeling. I mean, not being scary about modeling, because usually when we talk about modeling, we could imagine about complex mathematics, complex programming language, and so on and so forth. I think we are very lucky because in this current years, a lot of progress has been achieved in the way that programs, for instance, computational programs look like, right? Right now, so it's becoming more and more easy to develop scripts, right? To perform, for instance, machine learning models, or to analyze the data, experimental data by using machine learning models. And also it becomes more and more easy to also use computational frameworks, to perform simulations based on physics-based approaches. So my first advice is being open-minded, okay? Being curious as well. So, I mean, if you are curious and you want to learn about these techniques and so on, I will encourage you to do so. There are many books that are available. I mean, depending on, of course, on the type of scale that you're looking for and so on. For the scales I'm interested on, for instance, mesoscale and macroscale, definitely the book of Newman, John Newman, so professor in Berkeley University, so it's a reference, I mean, for particular for battery modeling. And then, so I think a lot of patience as well. I mean, as a student, when you work in modeling, because when you develop a model, it's not straightforward. So you will enter your parameters, your equations, and so on. But then it doesn't mean that the model will work straight away. So you need to be patient also to debug your model, right? And then to validate your model with experimental data and so on and so forth. Yeah.
Thank you.
Muchas gracias. Desafortunadamente el tiempo se nos acabó. La plática y toda la información que nos mostró es muy, muy interesante. Gracias por proporcionarnos el correo. Seguramente habrá oportunidad de que los que se encuentren interesados se comuniquen directamente con usted, perdón. Doctora Citlali, le cedo la palabra.
Gracias. Sí. Agradecemos a usted, doctor Luis Mendoza, y por supuesto al conferencista, el doctor Alejandro Franco, por su participación. Ahora